Just a quick video to cover the sorted list matching problem. We have two lists of last names where each of these lists has the same characteristic, namely, all of the names within each list are distinct and each of the two lists are in fact sorted. The problem is simple. We need to identify any of the names that are common to both of the lists. So here are two lists. List one, how many do we have here? 1, 2, 3, 4, 5, 6, 7, 8 names. List 2, we also have 8 names. We did not have to have the same length for each of these lists, the same number of names, but we do. But what did the problem state? That within list 1, all of the names are distinct, there's no repetitions. And within list 2, they're all distinct, no repeating names. Also, both lists are sorted. So now what do we do? How do we find the names that are common to both of these lists? What is the brute force approach, which is exactly where we should always start? What would you do to solve this problem? Pause the video and try to think about that brute force approach. In fact, it's a pretty straightforward approach. What would we do? For each of the names on list 1, simply do the following. Search for that name in list 2. If you find it, print, and then go ahead and break out of that loop. So that's really 2 for loops, right? So we have one loop that's going to loop over all of the names in list 1. And for each of these names, we start with Adams. We look for Adams in list 2. So we look for Adams, we look over all of these names, Adams is not found. Now we come to Bell, look over all of these names, Bell was not found. Come to Davis, look over all the names, we find Davis, we print Davis, and so on. This is the straightforward, slow, naive approach, which is where we should always start. So for each name on list 1, we search for that name in list 2. If the name is found, we simply print it. If the list is unsorted, the number of steps for A and for B will in fact be equal to the length of list 2. The number of steps required to basically search for the name in list 2 will be equal to the length, right? You're going to have to, worst case scenario, when I'm looking for, let's say, Bell, worst scenario, I'm going to look over all 8 names in list 2 when I'm looking for Bell in the list. Additionally, steps A and B, we run those steps for all of the values in list 1, right? So for each value in list 1, you're going to look for that name inside list 2. So what's the total running time? It's really the length of list 1 times the length of list 2. And if both list 1 and list 2 have the exact same length, let's call that n, the running time of this algorithm is in fact just n squared. But one more time to repeat that, here we have, I'm going to look for Adams. To do so, I'm going to look over all of the values in list 2. Then for Bell, I look for all the values in list 2. For Davis, I look over all the values in list 2. For Harding, I do the same thing. For Jenkins, for Lincoln, I look over all the values in list 2, right? So for each value in list 1, worst scenario, we're having to look over all of the values in list 2. This ends up being an algorithm with a speed or a runtime of n squared, where n is the length of one of those lists, and that's assuming that both lists have the same length. Now, if the two lists had different lengths, we would say the running time is the length of list 1 times the length of list 2. If we don't take advantage of the fact that those lists are sorted, that's the best that we have. It's going to be n squared. And here's going to be your code. It's a pretty straightforward code, right? You get the 2 for loops. We have this method called print matches. We have these 2 arrays of strings, list 1 and list 2. We're going to loop over all values in list 1. And then for each one of those values, we have a nested for loop to loop over all the values in list 2. If the 2 values are equal, so if list 1 at index I equals list 2 at index I, it's pretty straightforward, I know that. We're going to then print the 2 lists. We print the value that are equal between those 2 lists, and then we can go ahead and break, because we said the two lists have distinct values within a given list. So if we go ahead and we find a match, we know there won't be another match within that list. We go ahead and break and we continue. Pretty straightforward. But this algorithm does not take advantage of the fact that we said the lists are sorted. So how can we take advantage of that fact? How can we remember, the lists are sorted, how could that help us? And then we have a big brain moment. I'm enjoying my stream deck. We have a big brain moment. We're like, wait, I learned something with respect to sorting recently, binary search. And we say, okay, well, how can we exploit this fact? If we know the list is sorted, we can say, well, for every name on list 1, instead of searching list 2 via linear search, which is what we just did, let's instead search list 2 using binary search. When we're looking for a given name from list 1 in list 2, let's now use binary search. So that doesn't change a whole lot. In fact, the overall algorithm is going to feel similar. Here's what we had initially. We said for every name on list 1, do the following. Search for that name inside list 2. If you find a match, print it. Well, now, so here for step A, when we search for the name in list 2, we're not going to do that silly linear search. We're going to use a binary search. Let's assume, for sake of mathematics, to look at the running time, that both lists have the exact same size, which we'll specify here as size n. Now, we've seen, given a list of size n, or an array of size n, that is sorted, that's the condition of binary search. If it's sorted, to perform a binary search on an array of size n, what is the running time? It's log n. We've covered that extensively. We showed the math behind it as well. So given an array of size n, performing a binary search on that sorted array, it runs in log n steps as opposed to a running time of n steps with linear search. So with this binary search, step A really takes log n steps, but we now have to repeat that step A n times for each and every name in list 1. So the total number of steps is now, instead of n times n, where the second n was all of the linear search, now we have n times log of n. For each of the n values of list 1, we're going to perform a binary search, which has a cost of log n. So the total cost is n times log n, otherwise known as simply, you see right here, n log n. Now, as a student who's new to this, when I tell you that's much better than n squared, but it's hard to really see that, to feel that. So we want to really see how much faster this new solution is. Previous solution was O of n squared. This new solution is O of n log n. In about maybe 6 or so weeks, we're going to talk about what does this O mean. It really comes from big O. And as I mentioned, whenever you see me or hear me say O of something, that O really means worst case scenario that algorithm ran in n squared. Because of course we could have found a match right at the first person, right? The first name of list 2 could have been a match. But we're saying worst scenario, we have to go all the way over list 2 when doing linear search. So we say it's O of n squared. And for now, suffice it to say, let's just say that this O means worst case scenario. The big O running time, the worst case scenario is n squared. For this new algorithm, the worst case scenario is n log n. But how much faster is n log n over n squared? The easiest way to really visualize this is to use an example with numbers. Let's assume that n is 1 billion. If n is 1 billion, the first solution in the worst scenario would visit n squared values, which is 1 billion times 1 billion. I don't even know what that number is, but it has 18 zeros. It's huge, right? The second solution in the worst scenario would visit n log n cells, which we've learned log n, where n is 1 billion, log of n is 30. It's really a little bit less than 30, but let's call it 30. So n, which is 1 billion, times 30, that's 30 billion. huge difference between whatever this number is with 18 zeros and this number with 10 zeros. So a much needed improvement. And here would be our code. We're going to simply loop over the entire first list, and then we're going to perform a binary search looking for this value. So here we're starting at index 0 of the first list. We're going to look for this value, index 0 from the first list, inside the second list. So we're going to do a binary search over list 2, looking for specific elements that came from list 1. So this says, hey, if, and we're calling the binary search method, if this method returns true, meaning it was found, print it. Rinse and repeat. So we made it look nice by putting the binary search, by offloading that method into its own space to clean up this print matches method. But that's really it. This for loop runs n times. This binary search runs log of n times. And so for each one of these outer n times of this for loop, we have a cost of log n, so therefore a total cost of n log n. While we have seen binary search already, it is worthwhile to now see it with strings because we've seen it with numbers. So here is the code for binary search over strings. We're looking for this particular key, this particular name, within this array of strings that we called names. We have low as 0, high as names.length minus 1, the same while loop, while low is less than or equal to high. We calculate our mid, and then we check, hey, is the key we're looking for, is it smaller than mid? Well, how do you do that? You have to use the dot compare to. We recall if you compare two strings, if they are equal, it's 0. If one string is smaller than the other lexicographically, you will get a negative number. Otherwise, you get a larger number. We use those facts to then write this code pretty much identical to the binary search code we've already seen. The difference here is it's strings and it's using compare to. So that is our current best solution, a huge improvement. And here we are at our midpoint, only 12 minutes in. It's going to be a short video here. A little fail picture for the day. Is it funny? I don't know. I certainly wouldn't want to go down that slide. What a disaster. I hope this is just photoshopped. What a disaster otherwise. All right, sorted list matching problem. Can we do better than this? Of course, if I'm asking the question, you know we can do better. But how can we actually improve upon this? What can we do? Or what is the last piece of information or a missing piece of information that our last algorithm using binary search that we did not exploit, that we did not take advantage of? We did use the fact that list 2 was sorted. That's how we were able to apply binary search. But we also stated at the beginning of the problem that not only is list 2 sorted, but we said that both lists were actually sorted. But until now, we have not taken advantage of that. Until now, we did not exploit that fact, and the last algorithm worked regardless of whether or not list 1 was sorted. As long as list 2 was sorted, we did a binary search on list 2. It didn't matter if list 1 was actually sorted. But since it is sorted, we can exploit that fact. Think of how you would actually solve this on paper. Pause the video in just a moment and think about if I told you to do this on paper, forget code. What would you do on paper to actually, given these two lists, to identify the ones that are matching? And to help with this, let's actually come over here to the tablet and let's look at what we would not have done on paper. On paper, if we had atoms, are we on paper going to then do a binary search over this list and say, okay, where's the midpoint? Here's the midpoint. Is Adam smaller than Francis? Adams is smaller than Francis. Okay, let's now look at the bottom half of that array. The search space is now here. Where's the midpoint? The midpoint is Davis. Cool. Is Adams Davis? Are you kidding me? Would we have done a binary search in real life? Absolutely not. What a disaster. In real life, what are you doing? You're really going to be, I'm going to come back to the PowerPoint, and then we'll look at this as well in a moment, switch back and forth between the two. In real life, you would really have a finger almost like pointed at Adams, another finger pointed at Boston, and you'd like see, okay, well, Adams, Boston, Adams is smaller, so now look at Bell, Bell is smaller, now look at Davis, oh, Davis is now bigger than Boston. You'd really be like moving these two fingers down, and it'd be easiest if I could just point to these values. So I'm gonna come back over here to the tab. You'd really basically have a pointer right here, another pointer right here, and you would say, hey, which is smaller, Adams or Boston? Or are they the same? They're not the same. Adams is smaller. So you're going to move this pointer over here, and you're going to point to Bell now. You say, okay, well, are they the same? No. Which is smaller? Well, Bell's smaller. You're not really thinking all of this, but this is what's really happening in the mind. Then you come to here. Are they the same? No, Davis is smaller. Oh, so since Davis is smaller, you now know you need to come move this pointer, and you'd be like looking over here now. Oh, they're the same. So now you're going to print out Davis because it's the same. You have a match. And then what do? What you do now is you actually point, the pointers were here, the two Davises, right? So now what you do is you update both of the pointers, and you would have moved your hand down to both Duncan and Harding. Continue. We see, well, Duncan's less than Harding, so we need to update that pointer. We're going to make this one point to Francis. Francis is smaller than Harding, so we need to update Francis again. We delete this one. We'll make the pointer come to Gamble. Gamble is still smaller than Harding. We have no match. So we delete that one. We update the pointer, make it point over here. Now they're both pointing to someone called Harding. So we have a match. We print out Harding. We then need to update both of the pointers. And we're going to make this one point to Mason. This one point to Jenkins. There's no match, which is smaller. The Jenkins is smaller. We're going to update that. Finger is going to point over to Lincoln. And now Lincoln and Mason, Lincoln smaller. We would then make this finger no longer point to Lincoln, it points to Simpson. We come here, and now we're looking, and Mason is smaller, so we make Mason update, and now we point our finger on the right finger to Simpson. We have a match. We print Simpson, almost done. And we now update both pointers. This rightmost pointer is now done. It's really pointing off of the list. This left pointer is pointing over here to this person, however you pronounce that name. So in real life, the way you would do this is completely different than what we just asked the computer to do. So what can we actually take away from this? What do we recognize? Is that algorithm, we were really only going down those two lists of names. We were only moving downward, right? So if one was smaller, we moved its pointer down. It was still smaller, moved its pointer down. We moved our finger down. Finally, this was smaller. They weren't the same. We moved it down. Or that would that have happened? Oh yeah, it could have happened. Now we move this one down. Finally, there's a match. We move them both down, right? We only go down those two lists of names for every step, so to speak, until we find a match and we then print it. So the formalized version of the algorithm, you could say, would be like this. Start two markers, one at the beginning of each of the lists, and repeat the following steps until one of the markers has reached the end of the list. Compare the two names that the markers are pointing at. If they're equal, print, obviously, output the name. But if they're not equal, simply advance the pointer that is pointing to the name that comes earlier alphabetically. Advance it. And the one thing I didn't mention, if they are equal, we print it and we advance both of the markers. But if they're not equal, advance the marker that is pointing to the smaller of the two names alphabetically. That's it. Try to code that one up on your own and to see what you come up with. It's really going to be a while loop instead of a for loop, and think of some of the small nuances that would have to change compared to the previous code. But what's the runtime analysis? And this is where we want to end. How much of an improvement is this that we have here compared to where we were initially, asking the computer to do an n squared, two loops nested over everything, which is gravely unfortunate, improving that to use binary search, and now doing a binary search over list 2, but that's also something we would never have done in real life. So the takeaway here is that we realize it's better to think of how do we use what we would have done in our minds on a piece of paper and now translate that directly into code, and that's actually the faster algorithm in this case. The runtime analysis. For every iteration of that loop, we're really advancing one of those markers. We're moving down this list. Either this marker moves or this marker moves. Maybe it moves again, then this one moves, right? At every iteration, one of the markers is moving down the list. Therefore, the maximum number of iterations would be the total number of names on both such lists, which is simply n the length of those two lists. At each iteration, we're doing a constant amount of work. We're just comparing two names, which means this algorithm really runs in 2n total steps, where n is the number of names on the first list, right? So imagine if we kept moving like this marker moved, then this one, then this one, then this one, then this one, then this one. We would move through all of the names on both lists, which would be n plus n, which is 2n. Going back to that example, if n was 1 billion, that would only be 2 billion values compared to our previous algorithm, which was 30 billion values, or worse, the first algorithm, which was whatever that huge number was. That's it. We're done. Quick video. Time to practice some problems. Daily demotivator. It's horrible. Unique. I love the picture here, though. Come on. Just because you are unique does not mean you are useful. Horrible, horrible, fantastic demotivators. Love the dry humor. As always, take care, everyone. It's been fun.